This is another example of a partial pressure problem, and it is more difficult because it has a mention of mass. Some people will look at this and they will see that there are 75 grams of hydrogen sulfide and there are 75 grams of difluorine monoxide. Therefore, since there is half of each, the partial pressure of both must be 50% of the total pressure. So if the total pressure is 180 atm, then some people will think that the partial pressure of each must be 90 and 90 atm. Same thing with the volume. That is not the case because, as we said on a prior slide, volume, pressure, and moles are all directly proportional to each other for partial pressure. Double the number of moles, double the volume. Double the number of moles, double the pressure. Now, of course, volume and pressure to each other are inversely proportional, but this is not about the ideal gas law equation. What you do need to understand is that this does not transfer to mass directly. The biggest thing you need to know is that when you're given mass and have to do a partial pressure problem, you need to find the number of moles of each. Always get moles, and as I say in my class, the mole is the goal. So, determine the number of moles of each gas first. That is how you would be successful with this problem. So part A, we're going to determine the number of moles of each gas. There are 75 grams of hydrogen sulfide, and I'm going to turn those grams of hydrogen sulfide into moles of hydrogen sulfide using the molar mass as my conversion factor. 1 mole of hydrogen sulfide has a mass of 34.1 grams. My grams of hydrogen sulfide cancel, my moles do not, and I find that I have 2.20 moles of H2S in this container. Not my answer, but definitely part of getting there. I will do the same thing with the difluorine monoxide. There are 75 grams of that also. So 75 grams of F2O. I'm dividing that by the molar mass to get moles, and the molar mass of difluorine monoxide is 54. Doing the math here, I get another cancellation. Grams of F2O are gone, moles of F2O are not, and I have 1.39 moles of difluorine monoxide. Once you get the moles of each, you may as well figure out the sum of those two moles, which would be the total number of moles present. So, add these two together, and you get that there are 3.59 moles of gas total in this thing. And that is actually the conclusion to part A. Part B, determine the volume of difluorine monoxide that is present. So to determine the volume of difluorine monoxide present, we will use the parts over wholes idea again. There are 1.39 moles of F2O out of a total number of 3.59 moles. That is equal to, we are trying to determine the partial volume, so we're going to say V2O over, and the total volume is given way up here. The total volume is 2.5 times 10 to the third, which is 2,500 liters. Cross multiply, and you get that the partial volume, the volume of just the difluorine monoxide, would be 968 liters approximately. So that gives us an answer for part B. You could do the same thing to find the volume of hydrogen sulfide if you were asked to do so. Part C is asking us to determine the partial pressure of the hydrogen sulfide gas. So the same thing would apply, part over whole. Except now we're using the total pressure of the system. We have 2.20 moles of H2S over a total number of moles of still 3.59. And that is equal to the partial pressure of H2S, which I'm just going to use this symbology here, over the total pressure, which is 180 atm. Cross multiply, and you'll get an answer of 110 atm, which would be the partial pressure of the hydrogen sulfide gas. Just one more thing to help us round out the concepts here. If you were to find, or were asked for, the percentage of each compound, each gas, which they are compounds, of the total system, then you would just do 2.20 divided by 3.59, and in effect we find that this system is 61.3% hydrogen sulfide by volume and by pressure and by moles, and the system is 38.7% difluorine monoxide by volume, by pressure, and by moles. But as you can see, by mass it is 50-50. So if you were to sketch out what this would look like, it would be more than half H2S and then about 2/5 of difluorine monoxide. So when masses of a gas go into a confined space, they expand and are part of the molar ratio, not the mass ratio. That is the biggest thing to take away from this, in addition to the parts over whole concept.